morning, all of you. Today we have a distinguished faculty from IISER Thiruvananthapuram, and we are hosting the talk by Dr. Pramitha, and she will be giving a talk on introduction to atmospheric phase, water phenomena in atmosphere. She is a assistant professor in Earth, Environment, and Sustainable Sciences at IISER Thiruvananthapuram. And she has her major focus is on atmospheric waves, types, and related areas with atmospheric chemistry composition and atmospheric transfer and atmospheric circulation and related areas. She is also first rank holder in MSc Physics from Calicut University, and she is received the prestigious fellowships like faculty fellowship. She has many research publications, very high standard publications in areas like atmosphere, atmosphere, and southern stratosphere. So with that introduction, I invite Dr. Pramitha.
Good morning, all of you. So today I will be talking about this first introduction to atmosphere, and then to slightly into atmospheric waves. So you might be hear about this atmosphere and the introduction to atmosphere in the last one. So first of all, when you see Earth atmosphere, you consider Earth as a whole. The radius is around 400 kilometers. So in that, the maximum is atmosphere which contains is the homosphere that we live, that is up to around 100 kilometers. So when you consider this Earth as a whole, only habitable atmosphere only is 5 kilometers from the surface to around 5 kilometers. Maximum it is habitable atmosphere. That is, you can see that it is around 1.1280 distance from the Earth center. So you can see the ratio when you see the vertical and the horizontal scale. Atmospheric scale is around 100, height is around 100 kilometers, and when you see the total length of this Earth, so you can get it 2 by r, where r is the radius of this Earth. So total length when you calculate, it is around 4 into 10 raised to 4 kilometers. So when you get the ratio height to length, you can get that the height is very small as compared to the total length of this atmosphere. So this you may be knowing. Then when you comes to this atmosphere, the atmosphere contains different compositions like nitrogen, oxygen, carbon dioxide, water vapor, and trace amounts of nitrous oxide, ozone. And so we know that this around 78% of this atmosphere which contains nitrogen, and 21% of this atmosphere is oxygen, and 0.9% which comes carbon. Then comes other compositions like the carbon dioxide and other components. So when we consider this Earth as a whole, from surface to around 100 kilometers, when we consider the turbulent mixing is high. So when you see this nitrogen, oxygen, and the other gases, the composition can be almost around similar. If there is no source or sink for a particular species, whatever species you are seeing, that is around 80 to 100 kilometers, its composition will be same. That is, when I am considering an air parcel at the Earth surface, so it will be containing 78% nitrogen, 21% oxygen, and 0.9% other components. In the same way, when I go around the 80 kilometer angle, then air parcel, even though density decreases, but the air parcel, when I consider, the percentage will remain constant up to around 80 to 100 kilometer ranges. And above that, this turbulent mixing will not be there. It will be like a molecular diffusion will be taking place. So the region from surface to around 100 kilometers, that region we will be calling just homosphere, and above that region we will be calling it as a heterospheric regions. So in the homospheric regions, the concentrations will be almost similar. But above that, the molecular diffusion will be higher, and whenever the molecules with a higher molecular weight, that will come from the lower altitude, like from 100 onwards, it is based on the molecular weight it will be arranged. So at the end of this atmosphere, in the exosphere and all, it will be like the helium and hydrogen, the lighter gases. Based on the molecular weight, it is arranged. Then one of the main species is that carbon dioxide. So this you will be knowing this healing curve. So this is the carbon dioxide concentration from 1958 to 2025. That you can see that increase in this carbon dioxide concentrations, and this healing curve you might have seen in other classes also. So what is the reason behind that? There is a peak you can see in each year you can see. What is the reason for that? When you see any healing there, that is the carbon dioxide concentration is the year. Each year when you consider, there will be a dip will be coming and there is a peak will be there. Yeah, seasonal change. Yeah, which season it is higher? Summer season, yeah.
Winter season.
Yeah. The summer season, the photosynthesis rate will be higher. So there you can see a dip in the carbon dioxide concentration. And when it comes to fall and winter seasons, the decay rate will be high. So the amount of carbon dioxide which is releasing into the atmosphere will be increasing. So in seasonal, there you can see a seasonal cycle in a 1 year for this healing year. So that I told it that this when you go up to around 80 to 100 kilometers, the concentration will be almost similar. So this shows the carbon dioxide. This just for your information. This is the latitude altitude cross section of this carbon dioxide concentrations. So here you can see that as you go from 30 kilometers to around 90 kilometer altitudes, the concentration is almost similar. Above that only that concentration changes because this above that this carbon dioxide impact is solar radiation. The photolysis of carbon dioxide takes place to convert back into carbon monoxide and oxygen. So above that when you see, and also the above 100 kilometers, this molecular diffusion will be happening. So lower altitudes, carbon dioxide will be more. So this you can see in the case of other species also. Like if there is no source or sink, then your concentration means mixing ratio will be almost constant as you go upper in the altitude up to 100.
The ozone layer mostly concentrated in 25 kilometers. So there also CO2 converts in CO1 plus O1, O2 it will take one and convert in O3. So why I'm asking like really formally there.
CO2 interact with the this solar radiation which is in the wavelength of 120 to 210 nanometers. It is maximum taking place in the mesospheric altitude.
Not in
Maybe taking place but in the few rate. When you go to higher altitude, the rate is higher.
not in that. Sorry.
Yeah, it is.
But it's not also this is started from 30 kilometers.
Yeah, this is from time to saver data. So you can see that this is the for the complete climatology from 2002 to 2022. So the rate you know in the troposphere also it comes around 400 kPa when you combine these whole years climatology.
You have taken like meridional mean or just cross section?
This is a zonal view.
Zonal.
Yes, means latitude wise zonal. So that is the composition of this atmosphere. Then comes to the atmospheric pressure. So pressure is the force per unit area. So this pressure which is decreases exponentially from this surface to as you go to the higher altitudes. So when you consider this atmosphere, this mainly you can consider the hydrostatic balance. So in that case, atmospheric pressure means net weight above that layer. You can consider in the vertically when you consider the pressure decreases with the height. So then dp by dz equal to minus rho. So the net weight is balanced by this gravity. Here, when in the case of hydrostatic balance, there is no vertical acceleration we are considering. In that case, most of the case we can consider hydrostatic balance, but in the scale means length scale decreases. Like in mesoscale process and all, we should not consider hydrostatic balance. We should consider the non-hydrostatic balance in the case of mesoscale process. Then in the similar way, because of this gravity, air molecules are confined in the lower altitude. This higher number of molecules per unit volume you can see.
Sorry, I'm interrupting in between. Just now you told me for mesoscale process, this hydrostatic balance, we may not.
That is like means, hydrostatic balance when you are considering there is no vertical acceleration. So in that case, you are considering the weight is balanced by this gravity. So in the case of these tropical cyclones and all, vertical acceleration you should not avoid. So in that case, you should use non-hydrostatic equation. When you are solving for that system, these thunderstorms and cyclones and mesoscale processes, onwards you should use non-hydrostatic. But when you go in the synoptic scale, like a planetary scale things, then you can use this hydrostatic balance. So that you can check with each process with the depth scale, with the length scale, you can plot. And then when we say depth scale is comparable with the length scale, then you should not avoid this hydrostatic balance. Means you should not use hydrostatic balance. But otherwise, V by L ratio is very small, then you can use this hydrostatic balance. Then this is just you can just find out what is the mass of this atmosphere. If I am considering global mean of this atmospheric pressure is around 98.984 HPA, then what will be the total mass of the atmosphere? Just for your information, you should know just that number. You can consider Earth as a sphere. How much you are there? Yeah. Whether you use the 6,400 or registered was. It will be around 5 minutes, something like 10 to the power. So next we can see this vertical distribution of a temperature. So when you go to this mountainous region, you yourself can feel that the temperature is decreasing. So this shows that the temperature distribution is not constant in this atmosphere. It varies. So when you see the temperature in vertical distribution, you can divide this atmosphere into different layers, like the troposphere, stratosphere, mesosphere, and thermosphere. You can work out later. So you might have studied this in earlier also in the courses, this vertical structure of the atmosphere. So let me know what is the reason. This temperature in the troposphere, you can see that temperature decreases with the altitude. As you go means higher altitude, the temperature is decreasing. So what is the reason for this temperature decrease in this troposphere?
The sun is not hitting directly to the near to the surface due to convection.
Long wave radiation, because of that, the surface is getting more than.
Down. It cool down to condensation. That's why temperature is
Okay, in the troposphere, as the energy source is given to sun, so the sun is transparent to troposphere. So the sun directly heats the earth's surface and the earth will be emitting the outgoing longer radiation. So the source is not generally not in the top, it is from the down. So as you go upper means regions, then temperature will be gradually decreasing. So that's why the temperature in the troposphere decreases. So in between, this troposphere temperature is decreases, and as you go in the stratosphere, temperature is increases. Why is that?
Also on the forming processes and it's.
Whenever a species which absorbs radiation, then the temperature will be increased. This temperature means it is the average kinetic energy of a molecule. So whenever a species which absorbs radiation, then the temperature will be increasing. And whenever this emission takes place, then the temperature will be decreasing. So in the case in this between stratosphere and troposphere, you can see the transition region is known as the tropopause region. So means when you see the atmospheric mass, you have seen around 10 raised to 18 kilograms. So when you see this mass of this troposphere which is present, 90% of the mass, and you can see inside this troposphere. So when you see the height of this troposphere from polar region to equatorial region, when it comes, it is gradually increasing. Like from equator it will be higher, and as you go into this polar region, it will be gradually increasing. So this is the means tropopause values that you can see in this tropics. The tropopause when you study, this is the transition region between the troposphere and the stratosphere. So when you see in the tropical region, the average tropopause height is around 17 and 18 kilometers. Convection is maximum in the tropical regions. And as you go to the mid-latitude region, that tropopause height which decreases to around 12 kilometers. And into the polar region comes to around 9 and 8 kilometers. So when you see the tropopause height, it is gradually increasing from pole to tropical regions. So this tropopause study which is important because in the tropical region means the tropopause sphere region water vapor will be higher, and in the stratospheric region, ozone will be there. And tropopause is the transition region, so there will be transport of this water vapor from troposphere to stratosphere and ozone from stratosphere to ozone, means tropospheric region. So stratosphere troposphere exchange takes place in this tropopause region. So this tropospheric temperature study, you can see that you can use this radiosonde measurement to get the temperature profile as well as the cooling profile of this atmosphere, this tropospheric region. Mainly, you can get it in the stratospheric region also, but mainly you can use it in the tropospheric regions. Then this will be studied whenever an air parcel rises upward, the air parcel cools, and when it comes down, it is air parcel mass. So, what is the reason for that? You have seen this, right? Whenever an air parcel goes up,
Expansion or
yeah.
Increased by
No,
condensation.
I am asking about adiabatic.
Adiabatic means pressure will be expand, and once it will be expand, then kinetic energy of molecules will be there, and temperature will be down.
Yeah. In the case of radiosonde also, you can see that the pressure is decreases, so that balloon which goes higher altitude will be expanding. So in the same way, when you consider an air parcel, so this air parcel as it moves upward, the particles which is there, its volume will be increasing, expanding. So it is using its own energy for the expansion. So that air parcel which when it moves upward, it will be cooling. So in the same way, when this air parcel which sinks, then it will get pulps. Then this after this troposphere, there comes this stratospheric region. Stratosphere mainly is a stable layer. There is no convective activity takes place. So it is around 10 to 50 kilometers. That is depends upon which region you are, poles or equator or that. And 10 to 10 will vary based on which where is your tropopause. So the temperature will be increases with height from minus 60 degree to around 0 degree Celsius. So when you see in the stratospheric region, there is 90% of the atmospheric ozone which is present in the stratospheric region. So the value is around 8 to 10 ppm. This mixing ratio unit. So in the 25 kilometers, and then it decreases to around 2 ppm in the stratopause regions. So this stratospheric ozone, this you will be knowing this ozone layer in the stratosphere, where the oxygen molecules will be converted into oxygen atoms, and again it combines with the oxygen molecules and producing ozone. So it is main ozone production is taking place in the tropical region. When you consider more solar radiation is receiving over the tropical region compared to the other regions. And so the stratospheric ozone layer, you can see that UV radiation itself you can split into UV A, B, and C. So UV C from the radiation 100 to 280 nanometer, and the UV B is 280 to 360, and UV A is 400 nanometer. So you can see that the radiation which is reaching in the stratosphere to troposphere region is mainly UV A. That is the wavelength is lesser, means 315. Means higher, means energy is lesser, 315 to 400 nanometer range. So you can see that vertical profile of ozone when you consider, so the ozone will be maximum in the stratospheric regions. Then I have one question, like you might have heard about this ozone hole. So what is that ozone hole mean?
Ozone is present in
Yeah. So ozone when you can means vertical column you can take. So then the total means ozone in that vertical layer you arrange compress together. Then that thickness how much it comes, that is means a pure ozone thickness 0.01 millimeter thickness in the STP condition. It's a temperature in 0 degree and pressure in one ATM, that is unit is known as Dobson unit. So this 100 Dobson unit means 1 millimeter. That is, that thickness will be around 1 millimeter. So ozone hole, we are telling whenever this you measure the ozone, this vertical column ozone, which goes below 220 Dobson unit, then we will be calling it as an ozone hole. You might be heard this ozone hole only in the Antarctic or Arctic region, but not in the tropical region. Like we are telling this chlorofluorocarbon reason for this ozone hole, but that is main emission will be coming from this tropical latitude region. So why this ozone hole will happen in the Antarctic or Arctic? Arctic is lesser as compared to Antarctic. You may get the Antarctic ozone hole. What is the reason for that?
Something related to UV, some connection.
UV radiation. That's the translate because
This ozone hole that also you will be here like ozone hole forming only in the spring season, not in the complete year.
polar stratosphere is also
So there is like polar stratospheric clouds. Whenever there is in the winter season, the temperature in the stratosphere will be less. So when you compare the Antarctic and Arctic region, the temperature decrease means lowest temperature you can see in the winter season of Antarctic as compared to Arctic. So there is a possibility of forming polar stratospheric clouds in that regions. Then this chlorine, means the CFCs will be destroying this ozone. So chlorine you should get in the reactive form. So this reaction to take place, there is a surface is required. So this polar stratospheric clouds forms the surface for the ozone destruction reaction. Ozone destruction reaction to take place, there should be solar radiation. So after the winter season, when spring starts, this solar radiation also will be there, polar stratospheric clouds also will be there. So the ozone destruction reaction will be taking place most during that time. So in the tropical and other regions, there is no possibility of forming polar stratospheric clouds. So there is no surface for the ozone destruction reactions. Tropical. Even maximum ozone protection is there in the tropical region, but when you see the ozone concentration, it will be there in the polar region. Even production is maximum in tropical region. Maximum ozone you can see in the polar region.
So it will transport more or
Yes, there is a circulation which is called blue adoption circulation. So it will be transporting, there is a tropical air towards the polar region. So this ozone production, even though it is higher in the tropical, it will be maximum in the polar region.
ozone hole is also in the
Ozone hole which is happening after the spring season. So in the winter season, there is no solar line will be reaching into the this Antarctic or Arctic polar region. There is a around polar night set will be forming. Above that means around 66 degrees. Above that there will not be daylight. That air will be separated from that of the mid latitude air. There is no mixing will not be taking place. So there will be forming polar vortex. So that air, then this temperature will be very low there. The solar radiation also not reaching there. Then there will be stratospheric clouds will be formed. Then in the just after this winter, there will be slightly solar radiation will be coming. That time, this polar stratospheric clouds also present, and the solar radiation also there, and chlorine also there. So ozone destruction reaction can take place. So next is the mesosphere. So you might have studied what is the temperature profile we have seen earlier. In the mesosphere, temperature is decreases with height. So what was the reason for that? Less amount of gases means it is less amount of gases than in thermosphere also. The thermosphere is the temperature increases. It's there in mesosphere also. You also describe. So you heard about this carbon dioxide greenhouse effect. But you have to see that carbon dioxide, whenever a radiation which absorbs, molecule which absorbs radiation, then only temperature increases. When there is an emission takes place, temperature will be decreased. So when you go to tropospheric region, carbon dioxide is there. Carbon dioxide means any molecule when you consider, it cannot absorb all wavelength. There is a specific wavelength which can absorb maximum. Then only that transition will be taking place, energy level transition. So in the case of carbon dioxide, the peak wavelength it absorbs one wavelength comes to 15 micrometer region. So Earth is radiating means outgoing long wave radiation. The peak wavelength which is emitting is around 10 micrometer. So when you see the Planck's radiation curve, so it will be from 2 to some 20 micrometer region, Earth radiation emitting. So carbon dioxide which is present in the troposphere which will be absorbing the radiation emitted from Earth's surface. So that temperature will be increasing there. But as you go higher and higher, the temperature means the outgoing long wave radiation amount decreases. So when from the stratosphere onwards, what happens is that carbon dioxide molecules collide with other molecules. So it will be excited. So this excited molecule comes down to its ground level by emitting radiation. So it is losing energy. So the temperature decreases. So even stratosphere onwards, this is known as radiative cooling by carbon dioxide. So it is happening from stratosphere onwards, but stratosphere dominance is ozone dominance is there. Ozone heating is dominant there in the stratosphere compared to that of carbon dioxide radiative cooling. But when you come to mesosphere, the radiating cooling by carbon dioxide dominates. So the temperature in the mesospheric region decreases with height. Then another thing is that when you consider a particular location, the lowest temperature of that height wise, when you see the lowest temperature, you can see is the mesopause region. The lowest temperature not in the tropopause, it is in the mesopause region. That also, when you consider Earth as a whole, the lowest temperature will be coming in the mesopause in the summer pole. Because there exists a circulation in the mesosphere from summer hemisphere to winter hemisphere. So when you expect this temperature in the summer hemisphere should be higher compared to that of the winter hemisphere, but instead in the mesosphere the temperature in the summer hemisphere is lesser compared to that of the winter hemisphere. So when you consider Earth as a whole, the lowest temperature will be there in the summer pole of the mesopause. In a particular location, it will be in the mesopause region, and the lowest temperature in the whole Earth when you consider is in the mesopause, the summer pole region. Then this thermospheric region, it will be coming above that mesopause, that is from it starts from 85 to 100 kilometers, and gradually the temperature will be increasing. So temperature can go up to 1000 Kelvin, but this is dominated by solar radiation. That is, as I told, the molecular diffusion dominates above 100 kilometers, as well as density is decreases. So even though the temperature is very high, that mean free part which will be very large. So even you go to thermosphere, you will not feel that temperature. That the molecules which will be separated by distance will be very large. So, so when you see the thermospheric region, daytime and nighttime, the temperature will be higher in the daytime compared to that of the nighttime. Solar radiation has influence on the thermospheric regions. So these are the temperature distribution of this atmosphere. Then just for an introduction, there is you might have read books. There will be ionosphere also. Ionosphere, which is not a particular layer. And so you see that when around 60 kilometer onwards, there will be the ionization will be taking place. So electrified region of the upper atmosphere, we will be calling it as an ionosphere. So it will start from mesosphere and the main parts will be in the thermospheric regions, mostly electrified region of the atmosphere. So it will be affecting the AM radio waves signal. It will be reflecting during the night times. You can see the profile of this ionization density. So based on this ionization density, this layer we can divide into D, Q, and L. But that you can see only in the daytime. Here you can see this is considered it as a daytime. This is nighttime. So when you see this daytime, there will be different layers like a D layer, E layer, and F layer itself is divided into F1 and F2. But when you go to nighttime, there is no solar radiations, and when in the lower region there is a neutral components is higher. So it will combine with the neutral species. So the D layer will disappear in the daytime. This ionization will reduce. So in this E and F only you can see in the nighttime region. Nighttime. So next, just for an introduction, we say Earth has a magnet that you know. So you might have heard about this aurora australis and aurora borealis. So magnetic field is the region where the Earth's magnetic field influence is found. So you consider the left side is the solar radiation. It will be emitting solar photons and coronal mass ejection in highly charged particles. So when it interacts with the Earth's magnetic field, and it will be moving through these field lines, and it will be reaching in the polar region. You can see that interactions, and these charged particles is the Earth's atmosphere in the mainly in the polar region. So this you can see when there is a Lorentz force, these magnetic field interactions. So the path will be like that, into the poles will be this magnetic field, these charged particles will be reaching. So these charged particles will be interacting with the molecules present in there, and then it will be comes to a re-excite, so it will be producing light. So this nitrogen, oxygen, these species and all producing this red light and blue light. So you can see when you go to polar regions, this aurora australis, aurora borealis, you can see in the northern and southern hemisphere. So this is mainly you can see during the winter season, because winter season mostly this is in the polar region it will be night. In the 24-hour there will not be any solar radiation. So in that time you can see these lights very dominant as compared to that of the other seasons. This is the total temperature distribution. So then you so as you have seen this is just the atmosphere, how the density decreases, pressure decreases, and temperature decreases, and what are the main composition of the Earth atmosphere. This mainly we have seen in the vertical direction. Now we can see in the latitude and longitude wise. Latitude and longitude, which are the if you can divide the Earth into two equal halves, the central line that we will be calling it as an equator, and the northern side we will be calling it as a northern hemisphere, and southern side is a southern hemisphere. And the imaginary lines which will be connecting the two poles, north and south pole, that we will be calling it as longitudes. So from this you can see that these latitudes can vary from 0 to 90 degree in the northern hemisphere, 0 to 90 degree in the southern hemisphere. And the longitudes can vary from 0 to 360 degree. So you know that 24-hour comes when Earth rotates its own axis. So it is 360 degree it will be rotating. So each 15 degree will be corresponding to 1 hour. Then this you can divide the latitude wise. You can divide the region as a tropical region, midland region, and polar latitudes. So around equator to plus or minus 30 degree we will be considering is a tropical region, and 30 to 60 is latitude, and above that polar latitude. So right now we have seen the vertical distribution of temperature. So we can just see that is how it will be in the latitude as and altitude. So this you can see this will be the equator, and this is summer hemisphere and winter hemisphere. So as you know that this temperature, these temperature values are given in the this contour values you can see. And here this temperature decreases in the troposphere with high gradient. And as you go from equator to polar region, the temperature decrease that you can see. Also, this white line I just plotted for the tropopause. Like the tropopause will not be exactly like this. It will be like maximum in the region and decreases as you go to polar regions. So this when you see this troposphere, the temperature maximum in equator, as you go both poles, temperature decreases. And when you see in the stratosphere, you can see that the temperature decreases from the summer hemisphere to winter hemisphere. Like temperature is not maximum at the tropical region, it is maximum at the summer hemisphere. Whichever hemisphere has summer season, there it will be temperature will be higher, and wherever it is winter season, there it will be temperature will be lower. So here this maximum ozone will be there. I told in the polar region will be, even though ozone production is taking place in the tropical region, ozone is maximum present in the poles will be maximum. So this polar region, this ozone is the maximum, and the solar radiation also comes. So the maximum temperature in the stratosphere is there, and it gradually decreases the latitudinal rise. Then when you see the mesospheric region, so here you can see that this is the summer hemisphere. This shows the summer hemispheric mesospheric region, and this is the winter hemispheric mesospheric region. But if you will be expecting that summer hemisphere should be high means temperature compared to that of the winter hemisphere. But here you can see that the temperature is maximum in the winter hemisphere compared to that of the summer hemisphere. So there is a pole-to-pole circulation which is existing here, and that is because of these atmospheric gravity waves. So there will be an upwelling in the summer hemisphere and downwelling in the winter hemisphere. So upwelling causes the temperature decrease in the summer hemisphere, and downwelling causes temperature high in the winter hemisphere. So when you see the mesospheric region, there will be a temperature change, that is summer to winter. When you see temperature increases as it is
And this summer hemisphere and the winter hemisphere, both I'm just confused with the northern hemisphere and southern.
No, I didn't use a north or south. Here, whichever hemisphere, if it is a northern hemisphere summer, then you should consider this as a summer hemisphere, like a northern hemisphere. That time, other hemisphere winter. In that way, like I didn't convert it in a north and south. It is just like in the north is summer, then it will be like this, and this, south is summer, then south. This for just illustration. That is what I do. When you consider the summer and winter, like north and south, the temperatures in the stratosphere, it will not be same. This is for the illustration. Almost it will be similar like this, but the values small changes will be. But the distribution will be same. It will be like from which summer hemisphere to winter hemisphere. Stratosphere temperature decreases from summer to winter. Mesosphere, it is temperature increases from summer to winter. So this is the latitude altitude distribution of this solar region. So this is zonal wind when you see in the tropical region, means like tropospheric region, it is in westerlies. And when you see the summer hemisphere and the winter hemisphere, in the summer hemisphere it is like easterlies and it is here in the westerlies. This you can work out. You see there is a thermal wind balance. You might have studied. This temperature distribution you can calculate. Whenever there is a gradient in the temperature will cause and a vertical variation in the wind. That is the thermal wind balance. You can just read about that. So when you see this, you can link both plot, like earlier plot as well as this plot. Like whenever there is an like equator, it is maximum temperature, and from here to poles, it is decreasing. That time the winds are westerlies. But in the case of here, in the tropical means equatorial region stratosphere, when you go here, it is increasing, so there it will be becoming westerlies, and here when it decreases, it is becoming westerlies. So this is just this is the zonal wind distribution, where it is occurred, like when we tell about the waves, waves will be propagating. It like some waves will be propagating only in the westward direction. So that it will be depending upon the mean wind, how it is. So we will be just seeing that. So you should just know that in the summer hemisphere, stratospheric region, it is easterlies or westward wind. That you know, right? Easterlies or westward, from where it is starting.
Ma'am, the surface level, that equator tropical region is turning snow.
This is
It's somewhat high distribution or something, you know, ma'am.
yeah.
This one.
Yeah, this is not a particular location when you go, there can be changes. This is the global main level. Then you might have studied about this atmospheric equations. The atmospheric dynamics is nothing but the studying the motions of the atmosphere, which gives this weather as well as climate. So the fundamental forces acting on this atmosphere that we can calculate. Like atmosphere, we are considering it as a continuous fluid. So in order to consider means which are the forces acting on the atmosphere, you can consider one controlled volume. Then you can study the forces. So in the case of controlled volume itself, you can use both cases, like Eulerian approach or Lagrangian approach. Like if you take a volume, this you might have heard in the like when you take a volume, there will be some particles in it. So the control volume changes with the time. Like that is known as the Lagrangian control volume. That is particle inside will be same. If particle moves, the control volume moves with the particle. So you are studying about the same particles in the case of Lagrange. But in the Eulerian means that it is a fixed control volume. Particle comes and goes. Then the fundamental forces which is acting, which are the pressure gradient force, gravitational force, frictional force, and these are the means when you study the forces, first we can apply only Newton's laws of motion, inertial frames. We cannot apply it in a non-inertial frame. But in the case of Earth, Earth is a rotating sphere. So we means exactly we are telling it is not an inertial frame. But we can use Newton's laws of motion by incorporating like because of rotation, which are the forces comes that we can incorporate it and use the Newton's laws of motion. So those forces, because of the rotation of this earth, which are known as apparent forces. Other forces which are inertial forces, that is the fundamental forces. So the pressure gradient force, which gives as a minus 1 by rho gradient. That is the means which is from high pressure region to low pressure region. This pressure gradient force and direction. Then gravitational force, which is the means you know that acceleration due to gravity, that is because of the attraction of this Earth that comes. Then frictional force, that is the resistance to the flow. That is the frictional force. Then these apparent forces which are coming is the centrifugal force and Coriolis force. That is, if a particle which is stationary in the rotating frame, then the force which is acting on that particle is the centrifugal force. That is, means because of the rotation. In the same way, if the particle is moving, means accelerating in the rotating frame, that time what you experience is the Coriolis force. So this Coriolis force and centrifugal force that you can see in the dynamic meteorology. So this Coriolis force that you can get the means value is -2 omega plus v. So where is this particle oscillating? It will be having forces in this acceleration will be in the other two directions, not in the exact direction. So when a particle which moves in the northern side, then it will be deflected in the east side as well as in the vertical direction also it will be changed. So that you can see in the Coriolis force. Then because of the rotation we are getting the centrifugal force. So when we consider the gravitational forces and this centrifugal force together, then we will be calling it as an effective gravity. So this gravity force, when you see, it will be varying from equator to pole. So these are the main forces, like fundamental forces and apparent forces. This you can go through the dynamic meteorological content where you should study the relation between rotating coordinate system and a stationary coordinate system, and what is the relation between rotation and a stationary coordinate system. Then you can get the extra forces like apparent forces, and then you can include the initial forces there. So when you include all these equations, like all the forces together, then what you will be is the momentum equations for this atmosphere. So right now we know that which are the forces acting on the atmosphere. So atmospheric motions which are means like the system which is characterized by the basic conservation laws, conservation of mass, conservation of momentum, and conservation of energy. So conservation of momentum means momentum equation that you can use the Newton's laws, and this you will be getting when you do the rotating coordinate system. So when you go through the Holden dynamics, it is the derivations. So you will be getting these equations. So this is the momentum equations for the atmosphere. So here you can separate it out. That U corresponding to three-dimensional. So in a component wise, you can write each component, which direction, meridional direction, then vertical direction. You can split these equations. So you will be getting three set of equations for the momentum equations. Then this continuity equation. Continuity equation, this is just the conservation of mass. So if this air is piling up in some region, so it will be coming from some other region, and so this is the mass we cannot create. It's like it is always it is conserved. So that you can consider in a control volume how much flux means which is coming and how much is going, and when you equate both, you will be getting the continuity relation of the atmosphere. This also you should work out the Holden dynamics. Then the energy equations, that is the thermodynamic energy equations, that is whenever there is an energy source is there, it will be used to change the temperature. It will increase the temperature and it will expand or contract. Volume will be changed. So you will be knowing about the potential temperature. What is that potential
Temperature, the person is brought to the ground from the tables of the ground. Then that person is brought to the ground. How that is.
So what is the significance of that potential? When you see this potential temperature for anionic phase, Panaeromatic condition, it is a conserved quantity.
Conserved quantity and I'm going in deep like for dry air and moist air concept comes. So if it will be considered as a dry area, if moisture will come in picture, that's why we measure the potential temperature. Some technically I'm not getting the point, but we will take reference as dry air and we will calculate for the moisture. I think some
So potential temperature, even though we have temperature and pressure, we cannot tell the atmospheric system means how this pressure increases or temperature increases. It is like pressure increases, temperature variation can be different. Right? So both the together, that variations together comes in the potential temperature. So in the case of adiabatic processes, this potential temperature is a conserved quantity. So it is easy for explaining the some processes which is adiabatic. So whenever this conserved quantity is there, we can easily explain the process. Then next comes this hydrostatic balance, like you have seen with the balance between the pressure force and the gravity. So it is in the vertical direction, pressure will increase and then is equal to minus force. If the vertical acceleration is there, then you should not write like this. There will be an acceleration term will become. Here we ignore that term and we are calling it hydrostatic balance. So these are the when you complete set of this equation in order to explain the atmosphere as a whole, you require this Molecular equation, mass conservation equation, thermodynamic energy equations, and then you require these IISER equations. P is equal to rho r. So then this set of equations you have, then you can explain all the processes that is happening in the atmosphere. So next is the atmospheric waves. So as you have seen the processes that is happening in the atmosphere, that you can explain using the equations, that whatever equations are you have seen. So the solutions to that means you can see the different types of waves in the atmosphere. So before going to that, means, what are waves actually? Yeah, this disturbances or this transfers energy as well as momentum from one point to another point without the transfer of mass. So there you might have heard about the waves as well as oscillation. So what is the difference between a wave and an oscillation?
Travel from one plus motion allows direction of operation.
Yeah, means if the properties changes with the time and space, then it is disturbances which can propagate both space and time, then it will be waves. But in the case of oscillation, some oscillation like quasi-binary oscillations, that oscillation you can see it is in a particular space, but time-wise it will be varying. So there will not be spatial and time variation. Both variations are there, then we will be calling it as a wave. So here you can see that this is a pressure wave, that is the compression and the rarefaction of the atmosphere. These pressure waves, if I am talking here, it will be compression and rarefaction takes place and it reaches to. So here you can see that the red dot you can see. So that I am telling it as this particle which is oscillating. That red oscillation you can see. And but you can see that particle just oscillate there, but wave is propagating. Like means you should understand that is a wave which will not moves with the mass. Like the oscillations will be there, but the oscillations will give that energy to next particles, next particle. In that way, the waves will be moving, not like that mass particle moves. So that you can see from there. There is so these red dots, which red dot as you can see easily, that is, it is just oscillating. So when you consider the energy, it is transferring. That way, this energy transfer takes place. So this is just a terminology for these waves. So when you see these waves, like from the equilibrium position, the maximum peak height that we will be called crest or trough, at distance we will be calling it as amplitudes, and this frequency means number of complete oscillations. So that one complete waves in particular time per second. That is known as number of waves. That is the frequency. Then wavelength means the distance between two crests or two troughs. Right? That is the length for a complete wave. And how much time it took for a complete waves, that is known as period of the wave. Then phase velocity and root velocity. When you consider a wave, the phase of that wave which moves, that is known as phase velocity. Then a group of waves means combinations of the waves which will transfer the energy. So that motion that we will be calling it as a group velocity. So these are the main things. Now when you comes to this atmosphere phase, this atmosphere waves we can divide into this, different types like sound waves, mesoscale waves, and planetary scale waves. So when you see the sound waves, that we should not consider in the case of atmospheric waves. In the case of this compression and rarefaction of this atmosphere, which causes the sound waves. First of all, this is our mechanical waves. Waves to exist in this atmosphere, we require a medium for their propagation as well as a restoring force. Means any disturbances causes some restoring force has to pull it back towards the equilibrium position. Then only waves will be forming. Otherwise, this disturbance causes and it will be going as a disturbance to some other place. So, in the case of atmospheric waves, the medium for wave propagation is atmosphere fluid. And the restoring force, based on the restoring force, we can divide these atmospheric waves. So, this is based on the scales, and the sound waves, which are the because of the compression and refractions, we will be getting sound waves. And next is the mesoscale waves. Mesoscale waves, which is in 100 to 1000 kilometers in range, like horizontal scale. So that you can divide it into two, like internal as well as inertial gravity. That is, the restoring force is both gravity as well as buoyancy. So this you consider like an equilibrium position is there and a particle is there. Some disturbances like the convection or something, it causes the particles to just displace from its equilibrium position. So there should be like this force which has to pull it back towards the equilibrium position. Like means gravity, it will be pulling towards the equilibrium position. But as this particle comes towards equilibrium position, it comes with some momentum. So it will not reach up to equilibrium position, it will process the equilibrium position. So then when it goes down, then buoyancy will be acting, then it will again move up. So there will be waves as the time advances, waves will be forming in the atmosphere. So internal gravity waves, only gravity and buoyancy takes place. But in the case of inertial gravity waves, the period of that gravity wave is high, and in that case, Earth rotation also can play a role. So Coriolis force, that is 2 omega sine, that is particular to the that location, like latitude base. So that is inertial gravity. There also the gravity as well as Coriolis force comes to play. Then next is the planetary scale waves. Planetary scale waves, you can see that in the case of gravity waves, you can see it can propagate any direction, like westward or eastward or any direction it can propagate. As well as it will be moving both horizontal direction as well as vertical direction. Both direction it will be moving, and in In the case of gravity waves, it is not confined to particular direction. In what direction it is. But when you see the planetary scale waves, the length scale will be about 2000 kilometers, and you can divide that is mainly two types like the Kelvin waves and Rossby waves. In the case of Kelvin waves, the restoring force is gravity, but it will be forming over some boundaries, like in the equator region. Equator region, this Coriolis force changes from negative to positive. It comes zero at the equator. So in the boundary lines, these Kelvin waves will be forming. And the Rossby waves, which is vorticity, means it is vorticity you might have heard. That is the microscopic measure of the rotation of the Earth. So when you see this absolute vorticity in the barotropic atmosphere and potential vorticity in the barotropic atmosphere, so these Rossby waves are potential vorticity conserving motions. So the restoring force for this Rossby waves are variations in the potential vorticity. So it will be trying to pull towards the actual value. So because of that, the Rossby waves forms in the atmosphere. So mainly these atmospheric waves we can see the different types. Then when it comes to these atmospheric gravity waves, as I told, this gravity and buoyancy acts. But these waves to exist in the atmosphere should be stable atmosphere. That is, means if you consider this like this, Z is the equilibrium position for me. And the particle was at the time t equal to 0 and parcel was here. Then some disturbances caused, like convection happened. Then this pull means this particle displaced from here. As it goes higher altitude, it will be expanding. That is just schematically shown here. The size means volume will be expanding. So then as it goes higher, in a stably stratified atmosphere, a parcel which moves from its equilibrium position, it has a tendency to come back. So then this parcel will be coming, this is time t by 4. And it comes back. As it comes back, it will be overshooting its equilibrium positions and it reaches its lower position. When it goes below equilibrium position, then it will be positively buoyant. So then again parcel goes up. So as you see that time advances, the waves will be propagating. So this is a basic illustration of how these waves are formed. The same way here this gravity is the restoring force. Same way you can see for the other cases. So in the case of atmospheric gravity waves, the period is around 10 minutes to something minutes, and vertical wavelength from 1 to 30 kilometers, and the horizontal scale few tens to thousands of kilometers. So it can transport, as I told earlier, it can transport energy as well as momentum from lower region to higher altitude. So generally the source for these waves, which is considered to be in the tropospheric region, mainly topographic, convection, shear, etc. Sources for these gravity waves. So this can affect mainly the middle and upper atmosphere, and it can change the temperature and distribution in the upper atmosphere. So how we know that these waves are present? This is when you consider the radiative convective model for an atmosphere, this is the told area. You can see that in the mesospheric region we will be expecting, like this is during January. So January means the northern hemisphere, it is winter season. So this is the summer hemisphere. So here you can see that the temperature we are expecting is lower compared to that of the summer hemisphere, right? This is January month, so summer is in the southern hemisphere and winter is in the northern hemisphere. So based on the radiative convective model, this temperature will be lesser over the winter hemisphere. But as you can see that here, this is Stira observations, means like it will be having model as well as the observations in the model. So here you can see that the northern hemisphere during January, so this is the winter hemisphere. Temperature is higher as compared to that of the summer hemisphere. So means when you consider there is no dynamic space, like there is no wave space, then you should get that convective it's a radiative conductive photochemical model, how to predict in the same way we should get the temperature distribution. But instead, there is a dynamics place in the atmosphere where waves are present, so that we are getting the distribution different. Like instead of getting summer hemisphere higher temperature in the mesosphere, we are getting winter hemisphere higher temperature in the mesosphere. So, why we are studying these atmospheric waves, which can transmit energy and which can couple the different layers. From troposphere to stratosphere, mesosphere, we can couple these layers, and it can process this clear air turbulence, which is hazardous to aviation rescue, and as well as drive different oscillations. You just to see what is possible in an oscillation in the end of this class. So these waves can drive these oscillations. This is the means whatever I told, the seasonal variation of this temperature is higher in mesosphere region. So when you see the winter hemisphere, there will be means the temperature will be higher, and December, January, February, and this time this is northern hemisphere. You can see the temperature is higher, and the summer hemisphere means this will be lower. In the opposite way, when you comes to the southern hemisphere, winter season temperature is lower, and the summer season temperature is higher. It's exactly just opposite. Whatever you are seeing in the stratosphere, exactly opposite you can see in the mesospheric regions. So this is why it will be affecting the mixing of air and the oscillation which is present in the atmosphere and clear air turbulence, and this can affect the circulation, and mainly the wave-driven circulation, which is the lower dorsal circulation. Then I was telling like the condition for generation of these waves, the atmosphere should be stably stratified, so that you can get like when a parcel which is displaced from its equilibrium position, it should be higher, it should be negatively buoyant, and it is comes down, it should be positively buoyant. That you can get the condition that the potential temperature variation with the height should be greater than 0. That condition you can check like in the case of actual temperature also, as well as the potential temperature also. You can consider means you can go through that figure which is there in the essentials of meteorology. Like simple way they explain, like in the surface, if you take the parcels and at some altitude it is taking, so the temperature decreases in the environmental lab state also will be there, dry adiabatic lab state also for the parcel. So you can see how this stability exists. Means when the temperature of this parcel should be very less as compared to the atmosphere, then it comes back to its original position. In the same way, with the potential temperature also, you can get the equation. So there is the potential temperature in variation with the height is greater than 0, then the atmosphere is stably static. That you can check out, work out as in the tree. So these are the equations that we have already discussed. So when you use this momentum equation, continuity equation, thermodynamic equation, and equation of state, and this equation you solve with different approximations, you will be getting the solution for these other waves. These are the nonlinear equations. So you cannot solve directly. Means analytical solution is not there. So you should use some linearization. So whenever there is an means parameter is that there will be a main part as well as a perturbation part. That is, first of all, these waves we cannot see using any instrument. Whatever we can see is that some parameters, like temperature, these parameters we can get from these different instruments, and in these parameters we have to extract the waves which is present there. Otherwise, we cannot see the waves itself. So, waves will be moving, so that signatures we can see in temperature is all these parameters. So, I have wind information. So, I have to linearize that. That you can get the mean part as well as the perturbation part. So, use this into your all these equations, basic continuity equation, momentum equations. Use this linearization and use that whenever this perturbation term comes, then product of perturbation you can ignore. That value will be very less. So you can neglect those part and you can assume the solution for this as the wavy part. Using this, when you solve these equations as well as for getting these gravity waves, you have to use Gaussian approximation. That is density perturbation to the actual density, which should be very much less than 1. This rho 1, I mean that perturbation in the density, and rho 0 is the mean density. So, using this approximation also into your all these dynamical equations as well as linearization, and then you have to consider when the perturbation term comes multiplied with the gravity, that term you should not ignore. Like gravity means value is around 10 meter per second square, so that is a dominant term will be correct. Other than that, wherever the perturbation terms which is multiplying with other quantities like other perturbations, you can ignore. Then this you assume the solutions of these atmospheric waves in a wave part, then you can see the solution of this are like this. When you solve those equations, you put all these and just try out the solutions. If you want to solve this, you can follow this Chris and Alexander 2003 paper. So, using there, it has given the steps how to do this. So, whenever you do this, then you will be getting the solution. One of the solutions is that gravity waves. So, the dispersion relation, each waves, these gravity waves are there, Kelvin waves are there, Rossby waves are there. Each waves have its own dispersion relations. So, this omega is the frequency of that waves. K and M is corresponding to its wave numbers in the zonal scale, radial scale, and vertical scale. That is just 2 pi by lambda. Like lambda in the means in 3 dimension, you just component wise you can write. From there, just you rearrange where n square is the Brent-Weishala frequency. Brent-Weishala frequency is the natural oscillation frequency of this atmosphere. So, this vertical wave number you can visualize. Then F is the Coriolis parameter. That is F corresponding to particular latitude. This is equal to this by sin. So, when you see these gravity waves, this is for the complete gravity waves, like initial gravity waves as well as internal gravity. So, the frequency of these gravity waves will be in between Brent-Weishala frequency and Coriolis frequency. That is maximum value it can go up less to Brent-Weishala frequency, and the minimum value will be Coriolis. So these are the dispersion relation for these waves. So now when we study these waves, you can see that atmospheric density decreases with height. So that is just I have shown here with the parcel, which is when it goes up, then it will be expanded, just to show. So when you see these waves are there, so it is not interacting with the medium. So then this energy is conserved. So as you see these waves are moving upward, energy is conserved and the density is decreasing. So in order to conserve this energy, what should happen? That the waves amplitude to increase. You can see just like a waves energy is half rho u prime square, like half mv square. In the same way, you can see half rho u prime square. So when the troposphere you see density is higher, so the perturbation term will be lesser. As you go higher, density is decreases. So how much density decreases in the same amount, increase should be there in the u prime. U prime is the amplitude of that wave. So from here you can see that as you go into the higher altitude, the amplitude of the waves increases. So that the waves, generally these gravity waves and all, we will be studying in the higher altitude compared to that of the lower altitude. In the lower altitude, when it comes, the amplitude of the wave is lesser. So you cannot distinguish it from the actual values. So, but when you go higher, the amplitude is higher. So it is extraction we can easily do. So that we will be studying in the stratosphere and above the amplitude of the wave is higher. Then how this momentum transfer, this we have seen it will be like the particles which will be transfer its energy to the next particle, and the next particle in this way this energy will be, but not the particle. Particle will not be moving. Then transfer the energy as well as momentum. It happens. Then waves which will be interacting with this mean flow. Here you can see that just when a wave is there as well as this wind is there. This you can consider the wind speed. This altitude wise I just plotted the wind speed. So wave is there. Wave will be having some speed. Phase speed will be there. These are the different phase speed waves. So whenever a wave is moving, then there is no obstruction. Object is there. It's like a wind is not blocking, then it can go propagate up to higher altitudes. Then as it goes higher altitude, the amplitude will be increasing. And optimum value of amplitude, it will be breaking. Mainly the breaking of waves taking place in the mesosphere region. So, but in the case of here, the phase speed is 50 meter per second. So the this wave is propagating, and here it is the wind speed is matching here. Then the phase speed of the wave matches with the wind speed. Then this wave cannot propagate upward. There it will be breaking. So breaking of wave takes place there. So in this case, here c is equal to minus 10 meter per second. So this region, the wind speed is positive. So this is the westward propagating wave. Phase speed is negative. So the wave is propagating, and when it reaches the this phase speed will be equal to the wind speed. In that time, the wave breaking will be taking place. Otherwise, this wave can propagate any up to the mesospheric altitude. So that's the magnitude we can reach. So this is the illustration that I just wanted to show. Here this wind speed which is shown, that is in the green line. Just consider that. So here this wind speed is like this, but a westward propagating wave is coming and it will transfer its energy and momentum. In that case, it can change the wind speed from one direction to the other direction.
My name is clarification. I'm able to follow. This is a wind speed showing, and that down one you are showing us gravity winds.
Yeah. So this is for just all waves. It is like this. Whenever you are seeing any wave will be having some phase speed. So whenever wave propagates, when lower phase speed waves, it cannot propagate a higher altitude because in between breaking will take place because it will combine with the then somewhere this mean will be equal and there it will be breaking. So that will be happening. That is the mean flow interaction. Whenever a wave breaks there, if a wave is propagating upward, and here it is c is equal to plus 50 meter per second. So it is an eastward propagating wave. When it moves upward and when it breaks, it will be giving its eastward momentum to the background. So eastward wind can increase. So if it was a westward wind, it will be giving westward momentum and westward direction will be increase. So whenever this waves which is in higher amplitude also, it will be breaking. So whenever these waves moves upward, it can when it breaks in the opposite direction it comes and it breaks there, then it will be transferring eastward propagating wind and westward propagating wind breaks there. Then it can change even. It will be reducing the eastward wind and some point it can change the direction of the wind. So that you can see in the higher altitudes, these dynamics plays major role. Not in the troposphere you cannot see because amplitude is less. But when you see in the higher altitude, these waves can even change the direction of the wind.
So for studying this wave, we should take about troposphere.
In the troposphere also we can do, but the extraction will be difficult because amplitude will be very small as compared to like if you are extracting from temperature. So this from this temperature when you extract these waves, the amplitude will be around 0.1 or 0. That extraction will be difficult. But then when you reach the stratosphere and mesosphere, it will be somewhat higher, like 1 Kelvin, 2 Kelvin, so that we can extract like a meaningful amplitude wave. In troposphere also waves are there. Source region is in troposphere. Then it will be propagating to upwards. So when you do in the tropospheric region, above some 5-6 kilometer you can do because convection will be present there. So better to do above that altitude.
For me, this atmosphere part is little newer. I was an ocean. I am on an oceanographer. So in papers, I used to see in ocean also Kelvin waves across seas.
Yeah.
Kelvin waves used to propagate from west to east across the waves opposite. So that's the basic thing I know. But means I'm trying to relate it with.
Okay.
Thank you.
Then ducting and dissipation of the waves. Whenever this wave propagates upward, whenever its wave number, vertical wave number goes to 0, then these waves can reverse its direction without losing energy. So then means upward propagating waves are there, this wave is getting reversed. So these waves get ducted in that two regions and this wave can propagate in a higher distance in the length. Horizontal scale, it can propagate a longer distance. In the same way, whenever the vertical wavelength goes to infinity, that is the actual vertical wave, this is wave number, wavelength goes to 0, around 0, then the wave cannot propagate upward, and in that region, this wave amplitude will be piling up, and then there will be a breaking of these waves will be taking place in that region. That is known as dissipation, and earlier one which is known as the ducting. Then in the main sources of these waves, which we can consider, it is a topography, convection, and wind shear. So topography means any air parcel means displaced, like wind comes in the one side of these mountains and it displaces the air parcels. So then a stably stratified atmosphere, this oscillation which will be creating waves, and these waves that get from the topography. So these topography generated waves is mainly studied well. And next is the convection. Convection can generate waves like a complete spectrum of waves. When you can see that any convection taking place, this complete spectrum of these waves will be generated. So there we can divide it into three, like pure thermal forcing, mechanical oscillator, and obstacle effect. All these way we can separate the convection can generate waves. In the pure thermal forcing means these clouds will be forming, convection will happen, clouds will be forming, latent heat release will be there. So in that latent heat release, which can generate these waves, that is telling this pure thermal force. And mechanical oscillator effect means if there is a stable layer, like a tropopause or boundary layer, like if any displacement happen to these stable layers, like displacement happens, then there is an oscillation like waves can generate. That is why the mechanical oscillator. Another waves, this is like a moving mountain. Like when obstacle is there and wind is there, so then it can generate wave. So these are the even three mechanisms they are telling, but these are not separate. These are coupled together. Then another one is the wind shear. In these both cases, topography and convection, these waves will be generating from the source to higher altitude. It will be propagating higher altitudes. But in the case of wind shear, you can see some strong shear in wind is there in particular altitude. It can generate waves, and this will be propagating both upward as well as downward from the source region. So, least quantified wave source is wind shear. How wind shear generates waves. All other like topography and convection is almost we have studied most of the cases. So now, if you want to study this source of these waves, like there is a indirectly you can tell use holograph method. Another one is right tracing. This holograph method that is based on the polarization relationship of the gravity waves. We can plot this perturbation in the solar wind, horizontal wind, and vertical direction or temperature perturbations. From there, you can get that whether the wave is propagating clockwise or anti-clockwise. If it is propagating clockwise, it will be moving upward, and if it is anti-clockwise, it will be downward. So whenever you are seeing a gravity waves and then it is propagating upward, Then if you are seeing any source down, then you can see that this is the source for that. Another one is the direct method, that is ray tracing. That you can use that how the position and the wave number changes in the moving medium, like a three-dimensional medium, how this parameters changes with the time. That then you can use the dispersion relation of the atmospheric gravity waves. If you want to do more gravity waves, you can use the dispersion relation of the gravity waves, and you can get the ray tracing equation, set of equations for doing ray tracing, and then you can backward trace and get the sources for these waves.
Then they produce some broad clouds and some waves.
In
Broad
the
clouds.
yeah, that is in the topographic means generated waves. On the other side, we can produces the clouds. Then you are getting bored. He is checking time.
This is really
Sorry. We are going to so this is this extraction of this gravity wave. This is a simple illustration. That is, if you have any observations, like your observation is like this. Just compare this like a temperature. This is your observation. So this will be constitutes with the mean part as well as wavy part. So we should extract the mean part and then the wavy part. So here you can see that this observation, this you first you have to extract the mean part, then whatever left out is your wavy part. So if you have something like a radio sonde data, so you have this temperature profile. Then you want to extract the waves. So first you have to remove the background or mean part. So that mean part you can remove by fitting a polynomial, or you can take a seasonal mean or monthly mean. You can take and you can just remove. Then whatever left out, it will be the wavy part. That is the waves that we can extract. That will be easy when in the case of an observations like a particular location, like radar observations and in observations with the radar and all, it is easy, you can extract the waves. Then instruments which is used for this measuring this gravity waves. So from this MST radar, meteor radar, and all, you will be getting the information of the wind information. From the wind information, you can extract the waves from this MST and the meteor radars. And in the case of LIDAR, you will be getting the temperature profile. So from the temperature profile, you can extract these waves like just using. First, you have to remove the mean part, then whatever left will be the waves. Then airflow imager, which will be imaging the spheric region. So particular filters they will be using for each band, like OH emission will be taking place, ONE emissions will be taking place. So they will be using different filters and they will be imaging the atmosphere. So as a time wise, when they image, they can see the waves in that image. So from these images, we can extract the wave information. Then another one is the radio sonde as well as the rocket sonde. It will be getting the vertical profile of your temperatures and the wind information. So you have to use means some method like a polynomial fitting or a seasonal mean removal or monthly mean removal. Then first you should remove the monthly means mean part. Then whatever left is the wave part. Then satellite, this extraction of the waves from satellite, which is significant because we means in the case of like this radar as well as radar, it will be time wise you will be having information for a particular location. But in the case of satellite, maybe only one or two overpass per night. So you may, in order to extract this much small scale features from this one or two observation in a particular site in one day, it is very difficult. So we should use different techniques in the case of satellite. So another one means one special waves which is exists in the equatorial region, because in the Coriolis force changes its direction in the equator region. Because of this, there is a special case of waves which is exists, that is known as equatorial waves. So when you solve the whatever equations we have seen, then when you solve that means shallow water approximation, you will be getting the different types of equations. This is the special relation that you will be getting. So these for different meridional wave modes, you will be getting different waves. When this n is equal to -1, you will be getting a special type of waves, which are that we told as Kelvin waves. The things you can see that this is wave number versus frequency. So it is eastward propagating, like it means from 0 to infinity. So it is an eastward propagating wave. And in the case of n equal to 1, 2, 3, you will be getting different modes. Like you will be getting the solution as inertial gravity waves as well as the Rossby waves. So here you can see that Rossby waves which is moving in the westward direction. So the Kelvin waves which can move on the eastward direction with respect to the info, and the westward moving with the Rossby waves. And inertial waves which can move any direction, like eastward or westward. And another special type which is the mixed Rossby gravity wave. So mixed Rossby gravity waves, whenever the frequency is small, in that means the frequency is very high, in that case it will act as a gravity wave. Frequency is low, in that case it will be act as a Rossby wave. Like when frequency is low, in that case it acts as a Rossby wave, it will be propagating in the westward direction. And when frequency is higher, then it will be act as a gravity wave. So these special types waves we will be calling it as mixed Rossby gravity waves. So these waves we can see in the equatorial region. There is a Rossby waves, means mainly we will be seeing in the mid-latitude regions. So right now we have seen means overview of waves and different types of equatorial waves. Then this means as I told, which can drive oscillations. So this is the one of the oscillation which these waves can drive. That is a quasi-biennial oscillation. So this you can see in the equator regions. There is a this features you can see, like in the stratospheric region there is an alternate eastward westward wind pattern you can see. It's a period which is ranges from around 22 to 28 months. It is not an exact 22 months or 28 months. It varies with the years. So it is like a biennial means 24. So it is quasi-biennial. Like it can vary around 22 to 28 months. So here you can see that as we told this equator region, there will be Kelvin waves, Rossby waves, and this gravity waves. So when you see these are the waves which is responsible for this quasi-binary oscillation which is present in the stratosphere. So here you can see that there is a wind pattern and the wave is moving. First it was in a westward wave, so it will value which is matching with the background wind. So here this wave will be breaking. So in that case, this eastward means wind, it will convert back into westward, because westward waves which is breaking in that region. So wave become westward. So in that case, this eastward wave will be moving, propagating higher altitudes. But when this eastward move propagate higher altitude, when it reaches the higher altitude, here it may be breaking. So in that case, your westward wind will changes into eastward wind. So in that way, means this you can see. So this will be breaking in the lower altitudes, and then again it comes back to the eastward direction. So whenever this you can consider as a Rossby waves, and the eastward direction you can consider as a Kelvin waves. So the mixing means like both the action of Kelvin waves which will transport eastward momentum, and Rossby waves which will transport westward momentum, and in between gravity waves which plays a role which will be transporting both eastward and westward momentum. So in that way you will be getting an oscillation which is having eastward and westward changing winds in the stratospheric region, that is known as the quasi-biennial oscillation. This oscillation to exist in the atmosphere because of this special type of waves like equatorial waves and gravity waves. That's why we can see this quasi-biennial oscillation only in the tropical region, because equatorial waves is present in these regions. Then this is the complete picture of this atmosphere. So you can see that in the lower atmosphere, you can see this convection which will be maximum in the equator regions, and here we will be seeing the hardly circulations. So this convection will be taking place, air will be moving upward as it moves, reaches the tropopause, it will be moving in the both direction, northward direction as well as in the southward direction. And these parcels which moves in the northward and southward directions, it will be radiative cooling will be taking place. That is radiation to space. So its density will be, as it goes, its energy will be reducing, and it cannot move after some 30-degree angle. So it will be downward motion will be taking place in the around 30-degree latitude. So then it comes down, and from there it will be moving towards the equator. So this is known as the Hartley circulations, and this is purely thermally driven circulation, because the temperature means a increase, means a variation in the two latitude regions, so that is taking place. So this convection takes place, that region the rainfall will be maximum, and whenever there is a downdraft which is taking place, means downdraft means a hard descent, means downward motion taking place. Those regions mainly this Saharan desert and all will be coming over that region. Then this is same thing you can see in the polar region also. This is also thermally driven circulation, same as that of the Hartley circulation. And in between there is an indirect cell, that is known as the current cell. So this is the case for the tropospheric region. When you just go to the stratospheric region, that I told the Brewer-Dobson circulation. So this the main reason for Brewer-Dobson circulation, which is a wave-driven circulation, mainly which is because of the Rossby waves which is present in the atmosphere, along with that atmospheric gravity waves. So here you can see that these waves which will be pulling this air, just like a suction pump sucks the air towards it. In the same way, waves will be pulling this tropospheric means air from the tropical region towards the polar region, and then it will be sink over the higher latitude regions. So this circulation, this we will be calling it as a Brewer-Dobson circulation. So as you can see, this when you see the Brewer-Dobson circulation, winter hemispheric branch will be having higher rate compared to summer hemisphere, because you have seen, we have told like Rossby waves are responsible for Brewer-Dobson circulations, and you have seen the latitude altitude distribution of solar wind. In that winter hemisphere, it was eastward direction wind in the stratosphere. So these waves can propagate, and it can causes the pulling of this air, and the Brewer-Dobson circulation will be higher. But in the case of other directions, summer hemisphere, wind is eastward. So these waves cannot propagate upward. This was so this is the Brewer-Dobson circulation which is exists in the stratosphere. Then above that region there is means pole-to-pole circulation, that will be means upwelling happening in the summer hemisphere and the downwelling happening in the winter hemisphere. So that you have seen like the mesospheric temperature is higher in the winter hemisphere and in the summer hemisphere. So this is the latitude altitude distribution of this main dynamics of this atmosphere. Okay, so yeah, that's all.
Now floor is open to take some questions.